corroded pipe spool sits in a scrap bay, tagged for replacement. $500,000, 3 days of shutdown. But what if it's still fit to run? That decision has a name. Welcome back to the channel. At Jarasa Consultation Service, we work with the people who keep the process industries safe. And tonight, the question behind every inspection finding: what now? Fitness for service is a structured engineering evaluation. It asks one question: can this equipment, in its current damaged condition, continue to operate safely, and under what limits? The answer drives the classic decision: run it, monitor it, repair it, re-rate it, or replace it. Construction codes, the codes vessels, piping, and tanks are built to assume new undamaged equipment. They say nothing about a 25-year-old vessel that's suddenly too thin or cracked or fire exposed. Fitness for service fills that gap. The industry reference is API 579-1, ASME FFS-1, a joint standard organized into parts by damage mechanism, usually reached through the in-service inspection codes. For this video, we're assuming generic fixed equipment, pressure vessels, piping, and tanks in refinery or petrochemical service. Real cases always demand sites. Every fitness for service assessment follows the same workflow, and it never starts with math. Step 1. Identify the damage mechanism. Corrosion, thinning, a crack, a dent, creep. You cannot choose a method until you know what you're looking at. Get this wrong, and everything downstream is invalid. Step 2. Check applicability before anything else. Each part of the standard has explicit limits on equipment, materials, damage form, operating regime. Fall outside them, and that part cannot be used. Fitness for service is not a universal hammer. Step 3. Gather data in 3 buckets: design data, operating history, and inspection results. Data quality decides how far the assessment can go. Then select the part that matches the damage. Real equipment often needs more than one, and choose the assessment level, starting with the simplest. The output is never just pass or fail. It's a disposition: acceptable as is, with a remaining life and a next inspection date; acceptable with monitoring, repair, or replace. Every step documented, because a decision you can't defend on paper isn't a decision at all. The standard is organized by damage mechanism. Each part answers one specific question. Part 3. Brittle fracture. The risk that older, thicker, lower toughness steel fractures at low temperature during startup, shutdown, hydro test, or auto refrigeration. Usually this isn't an inspection find. It comes from comparing operating temperatures against material toughness. The question: is there enough fracture resistance at the coldest temperature and highest stress the equipment will actually see? Part 4. General metal loss. Broad, fairly uniform corrosion or erosion across a large region, found by ultrasonic thickness grids and profile radiography. The question: with allowance for future corrosion, is the average remaining wall still thick enough for the loads? Part 5. Local metal loss. A thin patch or groove surrounded by sound wall, mapped with thickness profiles. The question: is the thin spot small enough and the surrounding wall strong enough to keep carrying the load? Part 6. Pitting corrosion. Deep small area pits, chlorides, under deposit attack, tank floors, found visually with pit gauges and mapping. The question: are the ligaments between pits still adequate, and could a pit leak or start? Part 7. Hydrogen damage. In wet sour service, hydrogen collects at inclusions, forming blisters, or stepwise cracking, HES and SOHES, and mapping, and TOB, blisters you can see. The question: are the flaws sized and spaced so the remaining section stays adequate, with no risk of linking through the wall? Closely related are flat mill origin laminations and plate. They have their own part judged with the same logic. Part 8. Weld misalignment and shell distortion. Peaking, out of roundness, bulges from fabrication or from in-service events like settlement. Found visually with templates by laser scanning. The question: does the shape deviation add local bending stress or cut buckling resistance enough to matter? Part 9. Crack-like flaws, the most safety-critical part of the standard. Fatigue cracks, stress corrosion cracks, grown weld defects. Found by magnetic particle and penetrant testing, phased array TOFD, radiography. Accurate sizing is the hard part. The question: given flaw size, stress, and toughness, will this crack stay stable until the next inspection? Engineers picture the answer as a map with a safe region. One axis measures nearness to brittle fracture, the other nearness to plastic collapse. Inside the boundary, acceptable. Outside not. Part 10. Creep, range operation. Heater tubes, reformers, hot wall vessels slowly deform at high temperature. Evidence comes from surface replication, EIT, dimensional growth checks, and temperature history. The question, how much creep life is spent, and how much remains? Part 11. Fire damage. After a fire, triage is visual survey, portable hardness testing, metallographic replication, dimensional checks. The question, can this equipment safely return to its rated conditions? Part 12. Dents and gouges. Impact damage, excavation strikes, and dent-gouge combinations are the severe case. Found visually by dent profile measurement and with inline inspection tools and pipelines. The question, do the depth, the restraint, and any cracking or metal loss leave adequate pressure and fatigue capacity? And Part 14. Fatigue, cracking from cyclic pressure, thermal, or vibration loads. The question, will the projected cycles stay below a life-limiting level through the intended? Now, in the heart of fitness for service, the 3 assessment levels. Every damage part offers them. The same safety target traded against effort and data. Moving up a level removes unnecessary conservatism, never required safety. Level 1 is screening, typically performed by an inspector or plant engineer within the in-service inspection codes using minimal data, basic design values, a few thickness readings. The checks are deliberately conservative, so a pass is robust, low cost, often same day. Level 2 is engineering calculation. An engineer experienced with the construction code and FFS methods, working with fuller data, thickness profiles, measured flaw geometry, real material properties, corrosion rates, using standard closed-form calculations. Less conservative because real numbers replace worst-case defaults. Moderate cost and sometimes extra inspection is worth it, just to sharpen the data. Level 3 is advanced analysis. Specialists in stress analysis and fracture mechanics, with owner-user approval and peer review, using high-fidelity data and numerical methods, finite element analysis, detailed fracture mechanics, remaining life simulation. Most realistic, most expensive, justified when a wrong call costs a vessel or a shutdown. Here's the funnel. Every finding enters at the top. Most pass at level 1 and exit. Fewer need level 2. Very few, complex, high-consequence borderline reach level 3. A pass at any level ends the assessment. Remember, failing level 1 does not mean unsafe. It means the simple check could improve safe. It means ask a better question. When is fitness for service triggered? When an inspection finds wall loss below the required minimum, a crack, pitting, blisters, distortion. When operations stray, overpressure, overtemperature, a low temperature excursion, a fire, or a process upset that changes the corrosion environment. When service changes, a new fluid, new conditions, re-rating the equipment was never originally assessed for. When equipment reaches the end of its nominal design life and continued service needs justification. After repairs or alterations, confirming the equipment still fits its intended service. And for older equipment, built to superseded codes or with incomplete records, where fitness for service supplies the modern engineering basis. 3 duties. First, qualified personnel only. The standard itself defines what qualified means: construction code knowledge, damage mechanisms, inspection methods, and level 3 demands demonstrated specialist competence. Watching this video qualifies no one to assess equipment. Second, documentation. Data sources, assumptions, methods, results, remaining life, follow-up requirements. An undocumented fitness for service decision is professionally worthless. Third, the standard is copyrighted. Obtain it legitimately from API or ASME. We quoted no numbers tonight. Acceptance criteria mean nothing without their full context. This video is educational only, not engineering advice, and not a substitute for a qualified engineering assessment. Real decisions require the licensed standard, qualified people, and owner-user responsibility. So the next time a report lands on your desk with red ink on it, remember, the answer isn't scrap. The answer is a question. Thanks for watching. Stay curious and stay safe.